Here we are at video 6D. So looking at question 4, you should have attempted this already. Okay, I won't read through the question, you've read it through, and go through this fairly quickly. We have dt equals negative k t minus 29. So we recognise this as a Newton's law of cooling, and 29 degrees Celsius is the ambient temperature, and K is the rate at which it's cooling, and T, capital T, is the temperature at any given time. All right, so from, from this we get T, I'll be formal function notation, equals 29 plus AE to the negative KT. Now I'd just like to point out that A up here was used for ambient temperature, and here it's being used as just a constant. So we just accept that. Okay, so 29 degrees, that's the ambient temperature. We can see that this is always positive, assuming that A is a positive number. And so the long-term effect of this is to head towards 0, and so therefore of this is to head towards 29 degrees Celsius. Continuing. So if we put in little t equals 15, big T equals 271, can we find K yet? Let's see. So we get 271 equals 29 plus AE to the negative K lots of 15. And from that we can get AE to the negative 15K equals 242. So we can't get K yet, we have two unknowns here. Now luckily we have two pieces of information, so that means we're going to get some simultaneous equations that we can work with. All right, so I'll call that equation 1, and then our next bit of information, t equals 20, capital T equals 225. So 225 equals 29 plus AE to the negative K 20, and from that AE to the negative 20K equals 196. Right, that's equation 2. We've got two simultaneous equations. To resolve this, we're going to do division using index laws as our friend. So we'll do equation 1 divided by equation 2, and what happens there is the a's cancel out, and if we use index laws we get e to the 5k, so we've got negative 15 minus negative 20, e to the 5k equals 242 over 196, which gives us 5k equals 0.2108 ... and k 0.04216 ... I'm going to store that somewhere. I'm not going to store it in A. I usually store things in A, but we have an A floating around in this question, and I don't want the confusion. So I'm going to store it in C for constant, like K. And now I just need to create a bit more room for myself. There we go. Okay, so we found K. We haven't found A, so we can do that next. So in equation 1, you can have AE to the negative 15k k equals 242. Okay, I'm writing k, but we have a value for it. So a equals, if we multiply both sides by e to the 15k, so a equals 242 e to the 15k, and that's just calculator work now. So a equals 455.505 ... What do we ask for here? The initial temperature. So for the initial temperature, T equals 0. Put that in. T equals 29 plus a e to the k lots of 0. Okay. All of that is 1. So it's just 29 plus a. And so that is approximately 484.5 degrees Celsius. There you go. Right, so on a graph, I can't help myself, have to talk about a graph here. Sorry about the wonky scale. This is little t, this is big T, and the information given was that after 15 minutes, we had 271 degrees, and after 20 minutes we had 225 degrees. And we also had a differential equation, and that differential equation would imply a certain kind of slope field, but the problem is, without knowing k, it could imply infinitely many different kinds of slope fields. So we had some work to do. Okay, this is heading down towards an ambient temperature, heading towards 29 degrees, and there's the initial temperature that we worked back to find. Right, we had those two pieces of information, we found that piece of information. Okay, end of video 16.